Hello and welcome to this lecture. In today's lecture, we will talk about sensitivity analysis, when to use it, and how to build a sensitivity analysis plot, of course, because this will help us when making decisions. Now let's understand the context at which we use sensitivity analysis. Remember that sometimes you're making decision about things that will happen in the future. At this moment, you are considering what is the best alternative. Suppose you want to choose among building a small facility or a medium or a big facility. You're thinking about it now, but when you build the facility, this will happen in the future, okay? And you have some expectations about the future. Maybe the demand will be low, it will be high or moderate. So based on the expectations of the future, you are making your decision now, whether to build the big or the small facility. So what if the things that you were expecting it to happen in the future was not that accurate, okay, or didn't happen as you wished? So the sensitivity analysis will help us to know how sensitive our decision will be toward a certain factor. What if a certain factor changes by a certain percentage? What if the demand changes by 10%? Will increase or decrease? Will this remain the best alternative to choose at this moment? So sensitivity analysis will help us in this aspect. So it's very helpful to have some indication how sensitive the choice of an alternative is. And sensitivity analysis will provide a range of probability over which the choice of the alternatives would remain the same. So this will help us so much when making the decisions. Now we want to see how to plot a sensitivity analysis graph. Suppose this is our given. We have three alternatives, A, B, C, and we have two states of nature. When we want to draw the sensitivity analysis plot, it's very important to determine the range of probability of one of the states of nature. So we do not build it for both, we build it for one state of nature, and we need to determine which one are we choosing as a reference. So here we will choose state of nature 2, which is P2. Okay, and we want to determine the range of probability for this state of nature, okay, and see which alternative is optimal under this approach. So because we chose state of nature number 2, so when we are actually drawing the sensitivity analysis plot, we will have to draw the first state of nature on the left side, and the second state of nature, which will be our reference, it has to be on the right side. This is very important. So if you are plotting for alternative A, we have 4, it should be on the left side, and the 12 should be on the right side of the graph. Then we will connect them and make a straight line that will represent alternative A. So the plot will look like this. As you can see here, on the left side, we have the first state of nature payoff. At the right side, we have the second state of nature payoff. And we have the three alternatives, A, B, and C. They will be intersecting at some points. At these intersecting points, you can understand that the payoff for B and C are the same at this particular point. The expected monetary value for B and C is the same. Here, when A and C are intersecting at this point means that at this particular point, the expected payoff of alternative A and C are exactly the same. And we can see here that we have the probability. Remember, we chose to see the second state of nature, so we are showing the probability of having this state of nature, and its ranges from 0 to 1. Okay, So we need to first calculate the point at which we have the intersection between B and C. What is exactly the probability? And the same for the intersection between alternative A and C. We need to find these points. Why? Because these points will determine the ranges at which each alternative is the best. And remember, here we're considering payoffs. So of course we would like to see which alternative will give the highest payoff. So we should be looking at the highest line. Okay, so we determine this point. The value of it is probability of 0.4. So when the range is between 0, probability of 0 and 0.4, we should be looking at the highest line in this range, and here it is B. So if the state of nature 2 has probability between 0 and 0.4, then B is best. Okay, so you can see that what if we had low values for the second state of nature, and if the value was probability of 0.1, 0.2, 0.3, I still have a range that would tell me under this range, okay, even if we have slight changes, but we are still in this range, B would be the best. Okay, now what if we have a probability between 0.4 and 0.6? In this case, we are looking at the three lines. We see that C is the highest line, so C is the best in this range of probability. What if in this range the probability was between this point and 1? Then in this case A has the highest line, then A is the best alternative. So you see, here I'm testing the state of nature, the ranges of its probability. We always, when we have a set of alternatives and we have two states of nature, let's say here the demand is low or the demand is high, we usually give a probability for this state of nature. We usually say it is, let's say here 0.3 and here it is 0.7, because remember that the summation of the two states of nature equals to 1. So here, if it's 0.3, what if it changes to 0.4? So we see the range. Okay, so here I'm testing the sensitivity of this state of nature. What if it changes in the future? I still have a range that would guide me to say that even if it changes between this range and this range, B will remain the best. So this is the benefit of drawing the plot of the sensitivity analysis, because we can test how sensitive our or the factors that affect our choices can be in the future. Now now let's see how do we actually draw this plot. First of all, we will calculate the expected monetary value of each alternative. Okay, remember that we said that the probability of the first state of nature and the second, the summation of it equals to 1. Okay, so if this one was 0.3, then this one will be 1 minus 0.3, it will be 0.7. And we chose P2 as a reference. So when I want to calculate the expected monetary value, it will be 4 times the probability of the first state of nature plus 12 times the probability of the second state of nature. Because P2 is the reference, we will represent the second state of nature with a P, and the first state of nature, it will be 1 minus P, because their summation is 1. So with respect to the expected monetary value of A, it will be 4 times 1 minus P, it's the 4, times the probability of the first state of nature. We said that we will refer to it as 1 minus P, plus 12 times the probability of the second state of nature, where we refer to it as P, because this is our reference that is mentioned in the exercise. So I have this equation in terms of P. Now I want to draw the plot. So when P equals to 0, the probability is 0. Substituted in this equation, it will be 4 times 1 minus 0, so it will be 4, plus 12 times 0, so it will be 0. So the resultant of the EMV will be 4. Okay? So what happens with respect to our graph? When P equals to 0, I will plot the point 4. Then I want to see when P equals to 1. I substitute in this equation with P equals to 1. So 1 minus 1 is 0. So 4 times 0 is 0. Plus 12 times 1, it will be 12. So I have these 2 points. 4 at the left side. Okay. So at the left side, when P equals to 0, I have the point 4. And for the right side, when P equals to 1, I have the point 12. So when I combine these 2 points, I will have this line that represents alternative A. So we do the same for the second alternatives. What is the expected monetary value of B? It is 16 times the probability of the first state of nature, which is in this case 16 times 1 minus P plus 2 times the probability of the second state of nature represented by P. So again, we replace the values when P equals to 0. 16 times 1 plus 2 times 0, it's 16. When P equals to 1, 16 times 1 minus 1, so it will be 0. Plus 2 times 1, it will be 2. So on the left side, I have the value of 16. And on the right side, when P equals to 1, I have the value which is 2. So I combine these 2 points and this will give me a representation of alternative B. Same is done with EMVC. It is 12 times 1 minus P, 12 times 1 minus P, plus 8 times P. When P equals to 0, it is 12. When P equals to 1, it is 8. We combine these 2 points and we have line C. So this is how we plot the sensitivity analysis graph. Now, the second point is determining the intersection between the 2 lines. Okay? Now you might ask me, why don't I calculate all of the intersecting points? Suppose I calculated this intersecting points between line A and B, but you see that this point is lower than these 2 points, and we are talking about payoffs. So we are interested in getting the maximum payoff. So this point, okay, which is lower than these 2 points, does not change the decision. Okay, so we are not interested in calculating it. So it's better for me to look at the highest 2 lines in the graph, okay, and get its intersection. So here, this point and this point will determine the ranges that I have. Now let's see how do we calculate these points of intersection. Remember that at this point, EMV of B is equal to the EMV of C at this particular point. So when equating EMV of B and C, EMVB equals to the EMV of C. I put the equation for each one, and then we solve for P. The resultant is 4 equals to 10P, then P equals to 4 over 10, it is 0.4. Remember that this is the probability for the second state of nature. So I got the first point. The value of the point of intersection is 0.4. Okay, so now I have the first range, which is from 0 till 0.4. When the probability is between 0 and 0.4, B is the best alternative. Now let's calculate the second point of intersection. When lines C and A intersect, so the expected monetary value of C equals to the expected monetary value of A. Those are the values that I got from the previous slides. And when solving for p, 8 equals 12p, so p equals 8 over 12, so it is 0.67. So this is the point of intersection of A and C. It is 0.67. And this gives me the second range. So when the probability of the second state of nature is between 0.4 and 0.67, then in this case, C is the best alternative. And of course, when the range of the probability is after the point of 0.67 and increasing to the value of 1, so when it's in this range, then A is the best. So you see how the sensitivity analysis plot help us or guide us when taking our decisions, especially if we are afraid that some of the probabilities of the state of natures might change in the future, because this is something that is not completely certain to us. So the sensitivity analysis is very helpful in this case. So as a summary, we have this plot. In this plot, we will be looking at the lines. Where do they intersect in the highest points? We need to get these points because these points will help us determine the ranges. Now, I need to tell you one point. Suppose that these alternatives represented costs instead of payoffs. So in this case, you will be looking at the lines, okay, that are the lowest in each range. So in this case, I will be looking at the intersection of these two lines, not the upper one, because here I'm talking about the cost. So I will be interested in the alternative that will minimize my cost. So in this case, you will be looking at the points of intersection that are the lowest in this graph. So in this case, you will only have two ranges, a range from this point and 0, from 0 to this point, okay, you will be having a decision, and from this point till 1, you will be having only these two ranges at which you will be looking at the lowest lines that are the best alternatives. So suppose from this point and 0, we have these three lines. The best alternative will be alternative A because it will provide the least cost. And looking from this point of intersection till 1, so these are the three lines. In this case, you will see that the alternative B is the best in this case.